Hey everyone, it's Dr. Gilbert. In this example, we're going to look at a one-port capacitance that uses air as its energy storage medium. So we're going to analyze this piston cylinder, which contains an enclosed gas. And it doesn't really matter what gas it is right now. We just need to know that the volume inside of some sealed chamber is V. As the piston moves up, the volume increases. As the piston moves down, the volume decreases. The absolute pressure inside the chamber is P sub G for P gas, and the absolute pressure outside is atmospheric pressure. The area of the piston is given as A, and we're told that in the position shown, x equals 0, and the pressure of the gas equals the atmospheric pressure. So we're first asked to write the differential work, dW, as the pressure, volume, or moving boundary work done on the enclosed gas and the atmosphere. So we have to consider whether the work done is positive on the atmosphere and or positive on the enclosed gas when the volume increases by a fixed amount, infinitesimal amount dV. So the correct signs are shown. The differential work is minus Pg times dV plus P atmosphere times dV. We're next asked to write the stored energy as the integral of the differential work, with limits of integration from the initial volume V0 to some final volume V final. We are instructed not to compute the integral yet as a part of this problem, so all we have to do is make the substitution that the differential work is equal to P atmosphere minus Pg dV, and the limits of the integral are from some initial volume to some final volume. We're now told that in an adiabatic or isentropic process, the enclosed gas satisfies this constitutive equation that's shown. So P0 and V0 are some initial pressure and volume of the gas, so these are just some known values of pressure and volume. And from that, we can calculate the current pressure and volume, or the relationship between the current pressure and volume. The problem asks us to name the generalized power or energy variables involved, and what ideal one-port element this equation must represent. So since volume is a displacement variable, and pressure is an effort variable, this means that we're dealing with an ideal one-port capacitance. So we don't actually need to remember the thermodynamics here because it's given in equation 1, and from now on we can just consider this within our system dynamics framework as a one-port capacitance. So now we're supposed to actually compute the stored energy by evaluating the energy integral that we wrote earlier. So we have to substitute in the constitutive equation. We write that the integral is the integral of P atmosphere minus P0 V0 to the gamma V to the minus gamma dV. So here we've solved for the gas pressure and plugged it into this integral so that we have an integral with respect to the volume V. So the first term we can do in closed form. This is just P atmosphere times the change in volume. And the second term, we're going to have to use the power rule. So we raise the power to minus gamma plus 1, and we divide by minus gamma plus 1, and we evaluate at the limits from the initial volume to the final volume. So this is going to be equal to P atmosphere times the volume change, minus P0 V0 to the gamma, V final to the minus gamma plus 1 over minus gamma plus 1, plus P0 V0 to the gamma, V0 to the minus gamma plus 1, all over minus gamma plus 1. And we could simplify that last term a little bit, but we're not going to bother right now. The next part of the question says we should relate the volume difference, V final minus V initial, to the displacement of the piston. So here we just have to consider that the area of the piston sweeps out some distance, and so the change in volume is just AX. Next we make a substitution to rewrite the stored energy as a function of X. So we solve that equation 3.5, or from 3.5, for VF and plug it in to the energy equation that we found in the previous step. We get P atmosphere times A times X minus some constant terms times quantity V0 plus AX raised to the power of minus gamma plus 1, and then plus our constant terms at the end. Finally, we're asked to find the constitutive law between the piston's displacement, x, and the force F, which is necessary to generate that displacement. So based on our concept of a generalized one-port, we know that the force has to be equal to the partial derivative of the energy with respect to x. This is one of those energy relations that we saw in the class. The question says we could use any method, but that's definitely the easiest one. Finally, we're shown a graph of the correct answer. So this is a graph of the constitutive law where we have x plotted against force. And we're asked, why does it appear that there are asymptotes? There appears to be a horizontal asymptote as the graph proceeds with x going further and further to greater values, and it appears that there's a vertical asymptote. As x increases, the maximum pressure difference across the piston is going to reach P atmosphere because the absolute pressure on the inside of the cylinder can never be less than 0. This implies that there is a maximum possible force that can be exerted with the volume in the increasing direction. So with x increasing, the pressure difference can only reach P atmosphere. For this reason, the force approaches a horizontal asymptote as the displacement increases. The vertical asymptote is due to the fact that as x decreases, the volume inside the cylinder is approaching 0. Now we have a finite amount of gas that's enclosed in that volume, so when we try to collapse it to 0 volume, the pressure tends to go towards infinity. Of course, this is a non-physical result, and from chemistry we know that as the pressure increases, it's eventually going to turn into a liquid or a solid, but this simple equation does not capture that behavior, and so we see the pressure rising to or towards decreasing towards negative infinity, the force decreasing towards negative infinity as the displacement approaches minus 0.1 meters, which was the initial height of the volume. So we went through this problem pretty quickly. I'd encourage you to go back through, pause the video a few times, try to do these steps yourselves, and try to figure out how these concepts relate to the one-port equations that we've seen in the notes and in the textbook.